have our test rocket fired vertically from a well. Catapult gets it going, so it's shot up by a catapult. By the time it reaches ground level, it's traveling at 80 meters per second. Once it reaches ground level, the engines fire and it accelerates upwards at 4 meters per second squared until it reaches the altitude of 1,000 meters. At that point, the engines fail, the rocket goes into free fall. Now, by definition, by physics definition, free fall means an object is only influenced by the force of gravity. No drag or air resistance. Two ways to say the same thing. So gravity alone is acting on it once the engines fell. So two questions. How high does it go, and how long is the rocket in the air? Now, the kinematic equations we have, the equations that find position and velocity and time and all that, can be used if we break the problem into sections where acceleration is constant. The acceleration is not constant the whole time, but it's certainly constant during different periods. So right here, as it leaves ground level, it's traveling at 80 meters per second until it reaches 1,000 meters. During this section, the acceleration is 4 meters per second squared. So if we treat that section by itself, then we can use the kinematic equations. So, using the same approach we did on other problems, the variables that we have in our kinematic equations are these. We need to choose an origin to be in order to talk about position. So we need to choose some place to be x equals 0. Probably the easiest would be go ahead and call this ground level, the initial position, x equals 0, and just measure from there. So if we call ground level x equals 0, the final position will be 1,000 meters. We were told the initial velocity is 80 meters per second. We don't know how fast it's moving yet. We can certainly find that. Acceleration is 4 meters per second squared. And we don't know how long it takes for it to happen. So we know 4 of the 6 variables. We need to find out the velocity for sure, because that is going to be how fast the rocket's moving at this location as it continues upwards on its journey. So let's find the velocity. With these pieces of information that we have, looking through your kinematic equations, we have an equation that has all 5 of these top variables without time. We have the v squared is equal to v naught squared plus 2a x minus x naught. That will allow us to figure out the final velocity and how fast it's traveling finally. So v naught is 80. Acceleration is 4 meters per second squared. Final position is 1,000 meters. Initial position was 0, so I'm not going to write minus 0. So v will be the square root of this. This term, when we square it, is going to give us meters squared over second squared. This term, when we multiply it out, meters per second squared times meters, this is going to give us meters squared per second squared as well, which is good, because you can only add terms that have similar variables, or units rather. Once we take the square root of it, it's going to give us meters per second. Now, plus or minus, remember, we have to choose from. Which one's appropriate? Plus. So the speed, this ends up being 120 meters per second. So the rocket, when it's at this altitude, when the engines, I guess I shouldn't draw the engines firing anymore because the engines stopped, the rocket is now traveling at 120 meters per second. It's going to keep going. Now it's going to slow down now. Once the engines have fired, it can't speed up going upwards anymore. So it'll start slowing down until it reaches a maximum height.
So even though the rocket's still traveling upwards, it's in state of free fall.
Exactly. I know, a little counterintuitive, huh? So free fall doesn't mean you have to be falling towards the ground. Even though it's moving upwards, it's in a state of free fall once the engine shut off. And that's because it's under the influence of gravity only. Very good question. Okay, so now we know this. Since the second question is asking us about how long it's in the air time, let's go ahead and find the time it takes to go the first 1,000 meters. So we have two kinematic equations that have time in it, the position equation and the velocity equation. We really actually have information to solve either one of them, but the velocity equation is a little simpler to solve, so let's use that. So our time is going to be v minus v naught over a. So the final velocity is 120 meters per second. The initial velocity was 80 meters per second. Our acceleration is 4 meters per second squared. So 120 minus 80 is 40 divided by 4. Our time will be 10 seconds. So it takes 10 seconds for it to reach the altitude of 1,000 meters. Okay, moving onwards, we now can go ahead and change things up here. Let's now call this our initial, and the final being the maximum height. What was final before is initial now. So our initial position is 1,000 meters. Our final position, well, that's the first question, how high does it go? Our initial velocity is 120 meters per second. Our final velocity, 0, fabulous. Our acceleration, negative 9.8 meters per second squared. It's only under the influence of gravity now. We don't know the time, but we can certainly find it. It doesn't really matter which of these we find first. You can do either one, doesn't matter. If you want to find position first, we can go ahead and use the equation without time. Bless you. That's 0. We're looking for the final position, so we need to bring the v naught squared over, divide by the 2a, and then add the x naught. That'll give us our final position. So minus 120 meters per second squared, square all that, over 2a is negative 9.8 meters per second squared. Initial position was 1,000 meters. Unit-wise, we're going to get meters squared over second squared in here. We have meters over second squared here. So one of the meters cancels, both of the second squareds cancel. This term ends up having units of meters, plus meters. So the height, the maximum height, ends up being 1,735 meters. If you want to go with significant figures, you could leave it at 1,700 meters. Technically we have one. It's fine to be 1,735. You do need to have meters on it. Units are imperative. You will get points docked off on, say, a test if you do not have your units on your answers. So please make sure you get your units on there. So we know the maximum height. Let's find the time while we're at it, since we'll need to know that in terms of answering the second question. We can use our our velocity equation to find the time. Let's see, our final velocity is 0, so our time will be negative v naught over a. V naught, initial velocity, was 120 meters per second. Our acceleration is negative 9.8 meters per second squared. That ends up being 12.2 seconds. So far, the rocket is in the air 10 seconds plus 12.2 seconds, so a total of 22.2 seconds. Does that mean it's going to take 22.2 seconds to get back down? No, why not? Right. So the acceleration being different is going to change the velocities at the different altitude. Exactly right. Different acceleration means different change in velocity. So it's going to take a different amount of time to get to the ground. So here's the answer to the first question. The rocket travels 735 meters into the air. Let me write this here. So just filling in what we found out. Last piece of information we need to know is how long it takes to go from the maximum height to the ground. That way we can finish answering part B. Is it okay if I erase? So our last step. The maximum height is now our initial position. Our final position is right before it hits the ground, the impact location. So our initial position is the 1735 meters. What's our final position? 0. Our initial velocity was the final one before. Final velocity. We don't know. I'm so happy to hear you say that. Usually people say 0. Which, if you think about it, I mean, technically the rocket's going to hit the ground and come to rest. That is true. But what's the problem with using 0 as the final velocity?
It's a sit there and stays.
What caused it to come to rest? The ground, the earth. It ran into something. That's a different acceleration than gravity. We can only use the kinematic equations if the acceleration is constant throughout the whole thing. So our final velocity, this needs to be the impact speed. This needs to be how fast it was going as it ran into the ground. That way our acceleration is still negative 9.8 meters per second squared the whole time. Okay? So we're looking for time. We certainly can find the final velocity as well, but we don't need it. So the equation, our kinematic equation that has all of this stuff without the final velocity, is this one. The final position is 0. The initial velocity is 0. Solving for time, we're going to get negative x naught over here. Divide by the 1/2 a. So the square root of negative 2, initial position 1735 meters. Acceleration, negative 9.8 meters per second squared. So 19 seconds? Is that what you got? I just know what the total time is. I'm trying to do the math backwards. So the total time in the air is the 10 seconds plus the 12.2 seconds plus 19 seconds, which is basically 41.2 seconds. So that's the amount of time Total amount of time the rocket is in the air.